hello everyone. I don't think I know very many of you, so my name's Catherine. I'm based at the University of Manchester in the UK. So broadly speaking, this four-part session is going to be about numerical methods for forward UQ. So can I just have a quick show of hands? Who here, I don't know anything about you, who here works on some aspect of UQ and certain quantification? So a few of you, but certainly not the majority. Okay. So, let me explain my thinking in putting this together. So for me, the main aims of this tutorial, this is what I'm going to try and do, is explain, broadly speaking, what the concept of forward UQ is in the context of solving PDE models. I'm going to discuss broad approximation challenges from the point of view of numerical analysis. I'm a numerical analyst like Rob. I'm going to introduce a few different basic methods for constructing what we call surrogates. I'll explain that term a little bit later. And I'll sort of build up the level of difficulty with the end goal being to describe a state-of-the-art, or at least I think it's a state-of-the-art, we can maybe disagree on that, adaptive multi-level approach called the stochastic Galerkin method, which I'm going to talk about tomorrow. But I'm going to build up in terms of the level of difficulty. Since I don't know anything about you, I thought I would just start with basic. So this first session is going to be very, very basic, especially for the experts in the room. So my presentation style, I've sort of elected to be relatively informal with this. I'm not going to prove a lot of theorems for you, although there will be references in the slide where you can sort of follow up on details if you want to after the fact. My slides will be available at some point. I'll talk to the organisers about the best way to make the slides available to you. I'm not going to use the board very much. You can see I have quite a lot of slides. So don't worry, there are quite a lot of pictures on my slides, so they're not going to be dense with theory. But since I'm really only aiming here to sort of give you broad exposure to quite a lot of things, I would not recommend that you try and write down every single detail. The slides will be available to you. You don't need to take pictures or anything unless you really want to. So it's more just about getting the main points today, I would say. Okay, please ask questions as we go along if you think I'm talking total nonsense or something's not clear or my notation has gone to pot or anything like that. But as Rob said, since I have been scheduled slightly more time in the programme, we've got 90 minutes now before the tea break, and then there's theory another 90 minutes after that, but I'm only going to talk for an hour of that session, the second session. And then the final 30 minutes of that second session, Rob and I will just, you're going to be here, yeah? We'll just stand here and you can ask us questions. We haven't coordinated with our slides, by the way, so it might be that after I've said some stuff, now you've heard him say some stuff, things occur to you after we've both talked that you want to ask questions about. Okay, so please do stop me and ask questions as I go along if you want to, but if it's more like a general sort of philosophical question, maybe let's leave those till the end of the day. Does that make sense? Okay, so that's what I plan to do. Okay, so my assumptions about you. So when someone asks us to give a tutorial, we have to think, well, what do we think the audience knows? So I'm going to assume you know a little bit of basic probability and some linear algebra. Probably a little bit of functional analysis and at least how to define those spaces that Rob wrote on the board this morning. I'm going to assume, now it's not an assumption, I know you know this stuff now because Rob's been through it, right? So everyone has seen at least the weak formulation or the variational formulation of some PDE, especially the one in the box. I do use slightly different notation here and there. In Rob's notation, the diffusion coefficient was always A, and my notation is going to be K for some reason, or kappa, right? So you've all seen the weak formulation of this PDE. You all now know what the concept of Galerkin approximation is. All of the numerical methods that I will talk about have Galerkin approximation at the heart. So that's really a very important concept for everything I'm going to say. And I'm a finite element person by training. So I'm going to assume you know a little bit about finite elements, the H version of finite elements that Rob even drew this picture on the board for you this morning, and I didn't know he was going to do that, right? So in a sort of an H version of a finite element method, I'll just recap what Rob said. So let's assume our domain is a square. In a finite element method, we break the domain down into pieces called elements. Usually we use triangular elements as I've got here. You'll see in the mesh that I've got there, not all my elements are the same size. I'm an adaptive finite element person. When Rob had his lists of approaches, adaptive finite elements was on there somewhere, so I'm not a multi-scale person. I'm more of an adaptive standard finite elements kind of girl. So mathematically, with the finite element method, we often call our approximation pH. And mathematically, it's a linear combination of basis functions called phi I. I try to also keep to phi I for my basis functions. So in finite elements, if we use piecewise linear finite elements, then those functions would look like that. Piecewise linear finite elements on a mesh. Okay, and standard theory, let's just recap the main points. To summarize in a nutshell, if everything is nice in your problem, right, if your solution P to your weak formulation of PD is smooth enough, if regularity is not a problem, if your coefficients are not a problem, then you will be able to prove some sort of a priori result that says your finite element error measured in some norm. I've talked about the H1 norm and the L2 norm this morning. You'll be able to prove some nice result that says the error is bounded above by something that involves your finite element mesh size H. Right, and you'll have some constants in these bounds. So Rob was focusing on piecewise linear finite elements this morning, so if everything's nice, alpha might be 1. Right, we could use different kinds of polynomials. We could use piecewise quadratic polynomials or higher order polynomials. But if we want to get results like that for higher order polynomials, we're typically going to have to make much more assumptions than Rob made this morning, right? If you want more, you have to have more regularity, unfortunately. So when things are rough and badly behaved, then usually we work with lower order finite elements, right? So constant there will depend on the regularity of your problem. And as Rob's already said, this constant here could be hiding a multitude of sins if your coefficients have high contrast, short length scales, and so on. But just sort of close your eyes for now and go, it's some constant, H, some constant. Right? When we're working with finite elements, there are whole textbooks that you can read that will tell you how to prove error bounds that look like this. So that should be somewhere in the back of your mind as we're going along, okay? So I'm assuming, even if you don't know this stuff in depth, that you now have a little bit of exposure to it. Okay? Okay, so the outline for part 1, and if I've got too many slides, I'll just adapt later on. As I said, I'm just going to start slow, in case anyone never done anything with uncertain stuff before. I'm just going to set the scene to start off, just introduce a few PDE examples with some uncertain coefficients. Kind of give you the idea of the kind of problems that I work on. They're all fairly cartoon examples in the grand scheme of things, but they're all problems that are amenable to mathematical analysis, right? So just start to get you thinking about solving PDEs, common PDEs that arise in practice with uncertain input. Then I'll talk a little bit about spatially how we can mathematically represent or simulate spatially varying random coefficients with a focus on numerical methods. I'll talk about 2 broad strategies for doing that. So once you've got your PDEs, you've got a way to simulate random inputs. How do we do UQ? Then, if you've never done it before, this is probably the place you start. Basic Monte Carlo, basic finite elements. What could go wrong? Well, let's see. You probably already know what's going to go wrong, but it's probably the first thing you try if you've never done this before. Right? So it's worth just spending a little bit of time thinking about what goes wrong. So Rob's already said what's wrong with basic finite elements if you have these sort of badly behaved coefficients. And later in the week, Fabio Nobile will be telling you probably more about what's wrong with basic Monte Carlo as well. So bad sampling, bad discretization, what can possibly go wrong? Right? But it's a very, very simple method to implement, so at least that's probably where we should start. Where I'd like to get to at some point today is the idea of a parametric PDE. To start off with, I'm just going to have a PDE with some uncertain inputs, and then I'm going to sort of mathematically put some structure on my randomness and then convert my problems into so-called parametric PDEs. These days in the numerical analysis community, language has evolved a lot over the last 20 years. We tend to call them parametric PDEs these days, if we represent our uncertainty in a particular way. Okay? So that is my plan for the first part. We'll see how far I get. If anybody got any questions before I start? No? Okay. So let's just crack on and some PDEs with uncertain inputs. So I'm just going to introduce 3 examples to you. And I said I was going to focus mostly on computational details and implementation. So these are the examples, the model problems that I'm going to use when I demonstrate the methods that I'll talk about to you. So let me start with this one, which I'll call a groundwater flow model. So this is a coupled system of two PDEs, right, which relates to fluid velocity to a fluid pressure. So a very simplified model of fluid flow through a porous medium. So two solution fields here. And so typically, and this is sort of one of the examples Rob had this morning, we'll be uncertain about this coefficient, which will encode information about the permeability of the material through which your fluid is flowing, right? So things like oil reservoir simulation modeling, this model crops up a lot. Just a note about notation, slightly different notation to Rob. So he used omega for his spatial domain. That's pretty typical in finite elements. In the UQ community, it's not, because we tend to reserve omega for something else that you'll see in a minute. So D for domain, capital D for domain. And little d will be the dimension of my spatial domain. Little d will be mostly 2 in all my examples. Okay, so on my spatial domain, I've got a system of simplified PDEs. Okay, very simple, but sometimes we make the model even simpler by just combining those two equations together. We can knock out the velocity and just solve the problem with pressure. Right, so this scalar elliptic PDE, which numerical analyst's best friend, right? You go talk to statisticians and talk about this equation, they'll say, why the hell are you keep solving this problem, right? You solve this problem because it's the easiest one mathematically to analyze, in a nutshell, right? So we talk about this equation a lot. So where did this model come from? So the first equation is something called Darcy's law. The second equation encodes some sort of mass conservation constraint. Okay, so you might be solving in this formulation or in that one at the top. So that will be one of my model problems. Another one of my model problems is linear elasticity equations. So linear elasticity, you might think about this equation. The idea here is that sigma is stress or strain. It's the stress tensor. Stress is related to strain in some way, depending on what kind of material you've got. In a sort of simplified linear isotropic material, you have a relationship. So this thing is the strain. The strain depends on the displacement. So I've written it as if U is the thing I want to solve for here. When we're working with materials that are almost rubber-like, nearly incompressible, standard numerical schemes, things like finite elements, tend to have a problem. It tends to be quite difficult to compute stable approximations. Things blow up as one of the constants in this model approaches a certain limiting rate. So it's fairly common. So it's a very old model now, right? You can find the reference down here going back to 1965. We tend to call it the Herman model. The idea is to introduce a new variable, which I'll call P, which sort of acts like a Lagrange multiplier, sort of stabilization type term, right? Which is defined that way. So view this as, right, make P the subject. This is how P is defined. And we solve a coupled model instead. So we have a coupled system now of two PDEs. We've got two solution fields. One is vector valued. This time it's displacement, because we're modeling the deformation of the material rather than the velocity of the fluid. And we have another variable, scalar valued, which we sometimes call the pressure. And inside this model, we've got two key, well, sometimes they're constants, but more often than not, they're spatially varying as well, lambda and mu. In a course on elasticity, you'll know that they're called the Lemay coefficients. And the Lemay coefficients depend on two other quantities, E, which is called the Young's modulus, and mu, which is called the Poisson ratio. The problem is when the Poisson ratio gets close to a half, this becomes nearly incompressible. That's when standard numerical schemes tend to have a problem. Because if you see mu tends to a half here, something bad happens there. Okay, but this will be one of my models. So in this fluid flow model, we're generally uncertain about the permeability K, right? That might be uncertain in our model. In the elasticity equations here, we might be uncertain about these parameters. So why might we be uncertain about them? So, well, if we just have material in front of us, we can sometimes measure these things in a lab, right? But we might be thinking about materials that are, not available to us. They are in some component of some machine somewhere, or, and we just don't have access to them, or materials which might have degraded over time, even though we thought we knew what their properties were originally, but now they may no longer be that, and so on. So there's lots of reasons why we might be uncertain about these parameters. And then ramping up the level of difficulty, here's a model I'll show you some simulations for later on. This is a poor elasticity model. You can find some details in the papers down here. If you squint, you can see something that looks like my elasticity equations here, and something that looks like my fluid flow problem down there. Right? So this is a model that's used when we have materials that are both deformable, so elastic, and porous, so materials that are saturated with fluid, and then you want to model both the deformation of the material, and you apply a sort of force to it, but also the properties of the diffusive fluid flow within it. So this model is harder for a number of reasons, not least because it's got lots of different parameters in it, right, which vary on lots of different scales, right, and we might be uncertain about one or more of them, right? So we've got our Young's modulus and Poisson ratio, and again, we've got kappa K here, which is like our hydraulic conductivity coefficient, I think we call it in this scenario. Right? So you can keep going, right? You can make the problem as complex as you want. You go out there into the engineering world, you will find problems that are complicated, systems of PDEs. I'll say in the grand scheme of things, even though these look notationally dense, it's still simple in the sense that these are linear PDEs. I've got no time in these equations, right? So, already, they are sort of quite complicated in some sense, but still quite simple in the broader scheme of things. So I've got my three model problems here, right? All I wanted to kind of say is that, right, we've got some models, and we might be uncertain about some of the quantities that are the inputs to these models. I am going to focus on uncertainty being on the left-hand side of the problem, being in coefficients that are sitting inside differential operators or zero-order terms. We could, of course, have uncertainty on the right-hand side of the problem, in force terms, in boundary conditions, and so on. It's an extra layer of complexity we can add on afterwards. I'm just going to assume for today and tomorrow that my uncertainty is on the left-hand side of the problem. Okay, so we've got some PDE. Pick your favorite PDE in your mind and imagine that you're uncertain about one or more of the inputs that go into that PDE. So mathematically, how do we deal with uncertainty? If you don't like probability, close your ears now, right? So we're going to have to use some random variables, right? So mathematically, the way we deal, or most of us deal with uncertainty, is to model the quantities we're uncertain about as functions of random variables. Okay? This is why we need probability. And in the UQ world, so if you go to the SciArm UQ meeting, I assume it's happening this year, right? You split it into two parts, right? There's those of us who do forward UQ, and there's those people who do inverse UQ, and the inverse people go, well, you people are just doing the forward stuff, that's the really easy part, and it's true. Inverse UQ is harder than forward UQ, but I would always argue, if you want to do inverse UQ, you better make sure you know what you're doing for the forward problem. I'm only going to focus on the first part. So in forward UQ, this is what these sessions are about. The idea is this: you've got your PDE, you're uncertain about your inputs. You have to find, first of all, and this is another modeling step, some way to encode all your uncertainty about the inputs to your problem with some random model, which has a probability distribution associated with it, right? So you give me a probability distribution for your random inputs. Your task then is to propagate that through your PDE model and estimate quantities of interest related to the PDE model solution. So you're interested in predicting things or quantifying uncertainty in the PDE solution, given that you're uncertain about the inputs, right? So that's what we call it forward, going from the inputs to the outputs. In the inverse world, usually what you're trying to do is infer the things in your model you said you were uncertain about. You're trying to infer the uncertain inputs. And to do that, you're going to need to have some measurement, some data that's related to the solution of your PDE model, right? I'm not going to talk about this today. I'm going to focus on this thing at the top, forward UQ. Okay? So we're going to have some probabilistic description of the input for our models, first of all. Let me just do a quick simulation for you. So let's take that poor elasticity model. Okay, so I've got finite element code that I can use, good finite element code, or at least I think so, to discretize this problem in space. So think about material that's porous and elastic. Right, you stick it in a tank and you take a 2D cross-section this way. So on three sides, we've got zero displacement. Tank is open at the top. This is called a footing problem. We have another name, we call it the footing problem. The idea is you just press down on the top where that red line is. You squish it where that red line is. So it's elastic, right? So we've got some elastic properties of the material and there's fluid inside it. We want to model the sort of pressure of that fluid as well. So there were 5 potentially uncertain parameters in this model. I'm just going to pick 2 of them just to get things going. The Young's modulus and the thermal conductivity. So in general, these would be spatially varying. I'm not going to treat them as spatially varying here. I'm just going to pick them to be random variables. So what happens, or if E and kappa are random variables, so I'm just going to, this is just not because I think this is the correct thing to do, just to do a simulation. I'm going to model them as uniform random variables with some mean and some standard deviation. Right? Doesn't matter what. So the solution to my model then is then also random. My displacement is random, my pressure is random. So I need a method to do forward UQ to propagate the uncertainty in these quantities to the solution fields. I'll just show you a pretty picture. I've got lots of pretty pictures on my slides. So I have a method, and here what I'm showing you is an estimate of the mean on the left and the variance on the right of 2 of the solution fields. So the displacement is vector value, so this is just the vertical displacement. This is the fluid pressure. And I'm plotting the contours of these things on the mean deformed domain. So like my domain was like the material was like a square shape to start off with, and then it deforms when you press down on the top. So it kind of got this shape when the mean of the deformation leads to this sort of squished domain. And so in the UQ world, okay, so how are these helpful? Well, we might use the mean as our prediction, right? We might say, okay, here's my mean prediction for what the fluid pressure is. Here's my mean prediction for what the vertical displacement of the vertical displacement is. And then often we'd use the variance as some sort of assessment of the uncertainty in that prediction, if you like, right? P and U2 are random objects. They have a probability distribution. They're also spatially varying. So here you're looking at the mean fields, the spatial fields, and the associated variances. So in forward UQ, this is an example of forward UQ, right? I had a probabilistic model for my inputs, and now I've pressed the button, I've used some sort of code to evaluate quantities of interest related to the solution. I'm not claiming that these things are accurate. I'm just saying under the hood with some sort of method that I've used. I won't tell you what method I've used until tomorrow, but we are numerical analysts, right? So there's lots of questions we might ask here about what I've done and the accuracy of what I've done. Okay, so let me go a little bit further. So in this model, it was fairly simple in the sense that I had 2 uncertain inputs and they weren't spatially varying. Yep.
The question to the picture is, what's the grey area? Is that
the grey?
There's grey, but some parts aren't coloured.
So, okay, that's just to do with the plot. So the grey was literally just my deformed material. And then on top of that, I've plotted like the contours of this extra thing. So, so the pressure field is deformed everywhere. It's just imagine it's white, if you like. It's just to distinguish it from the background white square. It's just that deformed material, if that makes sense.
So there we have 0 vertical displacement, or?
I'm plotting the contours, something close to that.
Oh, okay.
Yeah, I mean, all I really wanted you to kind of focus on was like here, this is where the variance is high, which is no surprise, given that that's where I've squished it. Yeah, that makes sense. So we really want to focus for the rest of these sessions on spatially varying random inputs. Now and again, I might show you simulations with just non-spatially varying uncertain inputs, but just for now, let's focus on spatial inputs. So when we have spatially varying uncertain inputs, we tend to use the term random fields, although other people would use stochastic processes. Again, depending which community you come from, language might be slightly different. People who work in more spatial statistics tend to use the word random field. People who work more in machine learning will just use stochastic process. So you can use these words pretty much interchangeably, I would say. So what is a random field? In this context, it's a spatially varying random function. So here's why we need omega. To define a random variable, hopefully everyone knows we need a probability space. I'm not going to try and define a probability space. Probability space has 2 components. Omega is your sample space, P is my notation for the associated probability measure. Right, we have our spatial domain D, capital D, a random field, and this is the notation we'll use for spatially varying random variables. We say a random field is a random variable for each point in the domain, effectively. Right? So I think there's really three ways that you can think about a random field. You can just think about it as sort of one function, which has inputs from your spatial domain. And this is sort of a bit hand-wavy, but inputs from your sample space, right? It's just a function of both x and omega. X is connected to your spatial domain, omega is connected to your probability space. Or, as that definition sort of encourages to do so, we can think about it as just a different random variable at each point in our domain. Or, what's easiest for visualization is just to think about it as a collection or a family of spatial functions, if that makes sense. Right? So every time you pick an omega, effectively that's just shorthand for give me a new sample of the spatial function from this family. Does that make sense? So here sort of two pretty pictures. So on this side, the domain is one-dimensional. It's just the unit interval 0 to 1. I have a random field that I've simulated. I think I've got 10 different realizations of that spatial function from the probability distribution that I've chosen. So if I were to pick one point in my domain, let's say this one, and take a cross-section through here, at this point, z is a random variable, and here you have 10 different samples of that random variable. For each point, we have a random variable, and that thing has a distribution. So if I draw lots of samples, then I can build up an idea about what that probability distribution is. 2D, perhaps it's a bit harder to think about things visually, so now I have a unit square as my domain. I've got two pretty pictures. So in a lot of my slides, this is the way that I will visualize random fields in 2 dimensions. So it looks like an image. So think about this as a sort of a top-down, view of a surface plot. That makes sense? So I know this is not the way we're supposed, this is not the color scale that we're supposed to use these days. If you're a MATLAB person. It's the old style, and I'm quite old. So red is for a high value and dark blue is for a low value. Right? So I'm just showing you random fields, spatially varying random fields. So these two spatial functions on a unit square are both simulated from the same distribution. Okay, so I'm going to use this simple scalar elliptic PDE as my placeholder for PDE in a lot of my slides, just because it's easier to write out. So we start off with a PDE, right? And if we know all the inputs, if we know the right-hand side function, if we know the boundary conditions, we know the domain itself, right? Because in many applications, there might actually be uncertainty about the geometry of the problem that we're solving. I'm not going to deal with that. That's a whole extra layer of difficulty. So if we know all our inputs, and particularly if we know our diffusion coefficient there, kind of good to go. But now we say we're uncertain about that quantity in blue. We sort of have to develop our mathematical formalism, and this is usually then how we state the problem. Right? We have a random field now. Right? There's a distribution associated with that, a probability measure associated with that. Rather than saying, find me a function p, which is just a function of x, which that thing holds, now this is how we state the problem. Find me a random field, because the solution's a random field now, such that with probability 1, that's what that means, this sort of stochastic version of my problem holds. Right? As I've written down the model here, I'm assuming f and g are not uncertain, they're just some functions of x that I've chosen. Right? So we're going to go from thinking about problems that look like this to problems that we need to state like this. Right? So we have a probability measure behind the scenes, we have some sample space, right? And now we have a more complicated expression for our input to our model. Okay, so right before we do anything, put your hands up if you're a numerical analyst. Okay, most people. Okay, so let's think like a numerical analyst before we do anything. So we've got PDE, our inputs, and our solution are now random fields. What should we worry about? Or what are our challenges? First thing we have to do is worry about whether our problem is well posed or not. Alright? First thing, you cannot just take any old PDE and put in random inputs with any distribution you like and expect that to be a meaningful problem, right? Read papers about it all the time, particularly when you're doing simulations. Take some random generator, stick it in, see what you get. That's not going to be okay. So all of the sort of things that Rob was developing on the board this morning, we still need to worry about all of that, right? And we need to worry about it in the context of function spaces which make sense for our problem, right? So our function space is now going to be different because we're dealing with random or spatially varying random functions. So we have to go through all those sorts of thought processes again, right? So is this a well-posed problem? Can we write down it in weak form? What sort of weak form makes sense? What function spaces make sense, right? Does the solution exist? Under what conditions? Right, so for sure there'll be some conditions on K that will need to be satisfied in order to write down a weak problem which is meaningful, right? Once you can establish that it's well posed, what can we say about the regularity of the solution? We have to worry about that again. Right, again, just our regularity analysis, then different function spaces. We just have to adapt what we do. I'm going to skip over all of that, mostly, and just focus on numerical methods. I'm going to assume that the modes I have, and for the random inputs that I have, my problem is well posed, right? So I'm going to make sure that I did that and I took care of that. So what are we interested in approximating? So no one numerical method, hopefully everyone knows this, is good for all problems or for all tasks. That just doesn't exist, right? So our solution is a random object, so we might be interested in getting an approximation to the whole function, right? So P is a random, can I approximate this whole random object? Right? In other instances, we might just be interested in estimating quantities of interest evaluated. So maybe we're only interested in estimating the mean, say. And our numerical method should be tailored to what we want to do. Mostly I'm going to focus on this, but occasionally I will always do this. So depending on what it is you want to estimate, you might find that you need to tailor your approach to your quantity of interest. A priori analysis, right? So Rob sort of went through a lot of a priori analysis this morning, which says, okay, if certain conditions are satisfied, then I might be able to show for my chosen approximation scheme the error in some norm is bounded above by something. We have to worry about that here too, right? I'm not going to show you a lot of a priori analysis. I'm more an a posteriori analysis kind of person. Right? Out there in the real world, there will always be problems for which the assumptions you need to get this thing to hold are not satisfied. Right? Does that mean we shouldn't approximate the solution anyway? Not necessarily. In the a posteriori world, so I'm afraid everybody knows this term, the idea is you have an approximation, and you might be working in a scenario where you have low regularity, or where you're not expecting your numerical method to perform particularly well. But what we want is a mechanism for just estimating the error. That's useful in an engineering context, right? How large is my error? Right? Often we do work with methods that are not state-of-the-art all the time, but if we have some information that tells us how accurate our solution is, that helps us in some way. So there's lots of work to do for numerical analysts at every single bullet point here. Some people work more on this. I work more on this, I would say. So in my sessions, you're going to hear about numerical schemes, and tomorrow we're going to hear a bit about a posteriori error analysis. Okay? Yeah.
And what are the spaces for KP and F here that we consider? The function spaces.
Depends how you want to solve the problem. So I will develop that as I go along,
okay.
right? So that we can write down so sometimes you might just want to take one realization of K and solve the problem for one realization of K. Yes. That's exactly what Rob said this morning, right? So one instance of K. Depends how you want to formulate the weak problem, and I will develop that as I go along and I will show. So I'm not saying now what they should be, right? We'll see as we go along, right?
Okay, sure.
Does that make sense?
Yes.
Okay. It's good if you ask me questions because then I can take time to drink some more. So I'm just telling you here, think like a numerical analyst. Everything that you're worried about for deterministic problems, you have to worry about for these problems as well. And I'm going to focus on introducing some numerical methods, and I'll say a little bit about a posteriori error analysis tomorrow. Okay, so you want to do forward UQ. Let me park the PDE part for a bit and just come back to spatially varying random inputs. If I want to use something like a Monte Carlo method, like a sampling method, and once I've chosen my distribution for my random input, I've got to have a way to sample from it, right? Let's just look at some numerical methods that you could use to do this that hopefully are not too complicated. So just a word on terminology. I'm going to assume that my random fields, my random inputs are second order. What does that mean? It means that each point in the domain, the associated random variable, has finite second moment, finite variance, if you want to think about it like that. We're not dealing with white noise type things, we have bounded variance. Does that make sense? Second order. So that's an assumption that I make, even if I won't keep explicitly saying it. Again, just some notation. So mu is one of those sacred letters that we use for a specific thing. In UQ, mu always means the mean, right? So at each point in the domain, my random variable that's going into my problem has a mean. So mu will be the mean, and that might be constant. It might be the same at each point in my domain, or it might be different. So mu might just be a constant, or it might be a spatial function. Right, so when we model random fields, we have to pick the mean function, usually. That will be a piece of information that we need to simulate it. We'll need a lot more information than that. We'll typically also need the covariance function. So capital C will be my notation for covariance function. So whatever your domain is, 1, 2, 3 dimensions, you pick 2 points in your domain. Let's call them x and x dash. The covariance function is the function that tells us what the covariance of those 2 random variables is. Does that make sense? So 2 points in your domain, you've got 2 random variables. One way we sort of assess the relationship between the 2 random variables is with covariance or correlation. Okay? So the spatially varying random fields will need to have this. Right? Usually that will be a crucial bit of information and help us simulating the random field. You can't just pick any old function and call it a covariance function. It has to be symmetric. This is formally the definition of a covariance function. Right? This is the covariance between that random variable and that random variable. It has to be symmetric and non-negative definite. Another way of saying that is positive semi-definite. If you prefer that terminology, I'll say non-negative definite. Okay, so we'll typically always need the mean and the covariance. We'll also need the distribution as well, but we'll get to that in a minute. So just the notation, mu from now on is mean. It's a function in the function space setting, and covariance, again, which is a function, it's got 2 inputs, pair of inputs from your spatial domain. Okay, so if you want to get going with simulations, you're going to have to pick a covariance function. And here are just some standard models. You'll notice these are all continuous covariance functions. So if we have a continuous covariance function, then the samples that we draw will also be continuous in the mean square sense. So some of these are more common than others, I would say. So again, it's not important that you kind of crazily copy everything down. I'm just going to show you some common ones, so maybe you can come back to these later on if you want, when you've got the slides. So the one at the top is sort of a product of 1D exponentials. This one, I mean, it's a bit weird, isn't it, because they've all got exponentials in them. This one is often called the exponential covariance, so this is the 2 norm, or the difference between the points sitting inside there. This one is called the Gaussian covariance. It's perhaps more descriptive to call it the exponential squared. Right, so it's got the 2 norm squared here. And then there's another sort of broad family of covariance functions, which is sometimes called the Matern class, or the Whittle-Matern class, right, which looks much more complicated. I should say this is not the only way to write this down. There are different parameterizations of these kinds of covariance functions, which have different scalings here, which are more common in different communities. But I just wanted to show you this collection of functions on one slide, because hopefully you can see that these functions have parameters inside them. So we've got sigma squared here, which is representing the variance. So if you set x equal to x dash, that should give you the variance of the random variable associated with a point x. So if you set x equal to x dash in any of these models, you get the exponential of 0, so sigma squared will be the variance. So in all of these models, this would give us a random field whose variance was constant at each point in the domain. We also have these parameters L, which is the correlation length. Now that's going to be really important, especially in materials modeling. So in all of these models, you can see there's some sort of function of distance between the points that I'm working with. Right? So the L, this correlation length, basically tells us how fast the correlation decays as a function of the distance between the points. So what do you think is more challenging, small L, or big L? Yep.
Big L?
Small L. Small correlation lengths are usually a problem, right? In this model, this model is one that numerical analysts often work with because there's another parameter Q sitting inside here. And so rather than just being a single covariance function, this is a whole family of covariance functions, and this is really the smoothness parameter. Okay, so variance is really just kind of telling us about the sort of like the magnitude and the scale it takes. Correlation length is really telling us the length scale on which these spatial functions vary, and Q is telling us about the smoothness class of the realizations. So actually, with the exception of the first one, the exponential covariance and the Gaussian covariance are actually just special cases for this. So the exponential is what happens when we set Q to be, I've forgotten, is it? Well, some value of Q, I've forgotten, right? And so this also affects the smoothness. So by changing Q, you change the smoothness of the spatial functions that you draw with this covariance function. So all of these parameters will have an impact on the performance and the accuracy of the numerical methods that we develop. So just as a sort of a hand-wavy summary, low smoothness, small correlation length, and high variance tends to be hard class of problems. Low variance, large correlation length, high smoothness tends to be the easy class of problems from an approximation theory point of view. So we'll see some of these parameters again later on. Give me just a quick picture to sort of illustrate some of that. So I've got two different covariance functions, the exponential and the Gaussian. So Gaussian, because we've got the square of the 2 norm here, whereas here we only have the 2 norm. You have the Gaussian covariance, then when you draw spatial samples from a random field with this covariance function, you get spatially smoother functions. In other words, it's a higher value of Q. Right? So exponential covariance tends to give you very low regularity. All right, so hopefully you can see that the fields at the top spatially, got a pair of spatial samples, are rougher than the random fields that I have down here. So the selection of these parameters that I make is important because I'm changing my model class for the inputs that are going into my PDE. So if we've got low smoothness, we'll get spatially rough things in a nutshell. And then also, if you go from this column to this column, for each of these covariance functions, I'm also changing the correlation length. When the correlation length is smaller, the thing is varying, as I said before, on a length scale that's smaller. So smaller length scale tends to be more challenging. So working with things that look like this, high smoothness, large correlation length with respect to the length of the domain, tends to lead to easier computations than the ones up here with low smoothness and small correlation lengths. Does that make sense? Just as a broad point. Okay, so we pick a mean, we pick a covariance function. We have to do a bit more than that. Obviously, we have to pick a distribution, but I'll get to that in a minute. So if I wanted to generate samples to feed into my PDE model, how do I do it? So how did I draw these things? These are pictures, but actually these are functions, right? These are functions. So how did I draw these functions? So there's two sort of very broad approaches that we could take. So the first and the easiest thing to do is just sort of use a grid-based method. So if you remember all the detail that Rob went into this morning when he told you how a finite element code behaves, right? So what did he say? When you assemble your finite element matrix, you have to construct it by first constructing element matrices. To construct the element matrices, you have to do integrals, and your coefficients are sitting inside there. How do you compute those integrals? With quadrature at the end of the day. So the information you need from the coefficient that's going into your problem, you only need to know its values at a set of points. So this isn't a crazy thing to do if you're using something like a finite element method, where you really only need access to samples of your random inputs at points on a grid, on a finite set of points. So the first thing we could do is stop thinking about functions and just thinking about the value of the function at a finite set of points. That's what I mean by grid-based representation. So let's say I've got a random field, bear in mind this is something I want to put into my PDE model, chosen a mean, chosen a covariance function. In the grid-based representation, we say, okay, I don't really need to know what z is everywhere. I only need to know what it is, and I only need to be able to draw samples of it at a finite set of points. So x1 up to xn, let it be some points in my domain, so maybe it's these points, maybe it's these points. There might be quadrature points, there might be vertices on my finite element mesh, whatever. So each point, my random field is a random variable. Take those random variables, stick them into a vector. And then we've got a vector valued random variable. Yeah.
So just that I get this bigger picture, like we don't have a random field.
You do have a random field.
Okay, but don't we then automatically have the covariance and the mean? Because to me it seemed like we choose this to be something. The covariance.
Forward you have to choose the distribution that you want to propagate forward through the PDE.
Okay.
So my starting point is z is a function. And I have a mean function and I have a covariance function, and now I just want to get into, well, how would I draw samples of it, right? So if I'm only interested in samples of my random field at set points, then it's now a random vector, and as a random vector, as a vector valued random variable, or a multivariate random variable if you want to call it that, it would then have a mean vector, and your mean vector, the components would just be your mean function of the field that you started off with, evaluated at each of these points. So you can construct this vector if you knew that, if you chose this function. I'm saying the starting point is you know this, discretize your thing on a set of points, and the associated vector you just get by evaluating your mean function at a set of points. It's very easy to prove that that's what the random vector would be. Does that answer your question? And similarly, once we've evaluated it on the grid, it has a covariance matrix now. The random vector has a covariance matrix rather than a covariance function. And if you do the math, you can show pretty easily that the entries of the covariance matrix are just whatever your covariance function was evaluated at that pair of points. Does that make sense? If you wanted to just start in the vector world, you could do that. But I'm just assuming we started in the function space world. Okay?
Yeah.
Yep. So I'm not assuming we have any data, by the way, right? Which is just saying I'm starting from a probabilistic model for my random field. We might have data, so let's say my Z here was my diffusion coefficient. Maybe I have some limited measurements of it somewhere. Usually the way that we would use that is to help us inform the choice of the mean and the covariance function. Right? So in the vector space world, we're working with a matrix. A matrix for the covariance and a vector for the mean. Covariance matrix, again, its properties, it's symmetric, and it's non-negative definite, or positive semi-definite, if you prefer that term. So if we work in the grid-based world, then everything's just linear algebra, effectively. It's not that we can forget about probability. Probability is there, but doing computations really is a mix of some basic probability with some linear algebra. So far, I have not said anything about distributions. Right? You can't just take a mean and a covariance function and say that's my random field, right? You've got to specify the distribution. So, for now, I'll talk about Gaussian random fields only. What is a Gaussian random field? Gaussian random fields are special. We say a random field is Gaussian with a mean function mu and a covariance function c if, no matter where you evaluate it, and no matter for how many points you evaluate it at, the associated vector is a multivariate Gaussian random variable with mean vector mu and covariance matrix Cn that I just defined. It says the finite dimensional distributions are multivariate Gaussian, basically. That is the definition of a Gaussian random field. And because of that, it tells us that Gaussian random fields are uniquely specified by their mean and covariance functions, which means that it's the easiest class of random fields to do simulations for, effectively. So hopefully everybody knows what a multivariate Gaussian random vector is. I'll just put that on the slides just so everyone's clear. So So for instance, if we wanted to compute the expectation of a function of a random variable that's a multivariate Gaussian, we have to integrate with respect to the associated probability measure, which we can write as an integral, a weighted integral where this is the associated probability density function. Right? That's what it means to be Gaussian. Okay? So if I want to generate samples of a Gaussian random field that have been evaluated on an endpoint grid, in theory, all I have to do is have a method for generating random vectors from a multivariate Gaussian distribution with whatever mean I want and whatever the covariance matrix is. That makes sense? So pick your mean, pick your covariance functions, evaluate them on your grid, and you've got your covariance matrix and your covariance and your mean vector. Okay, and that was how I plotted those pictures, right? We use a grid-based method. So here and there on my slides, I said, here's a simple exercise you might want to try. Don't have to do it now, but when you get the slides, if this is new stuff to you, then maybe this is somewhere that you can start. It's a very simple recipe to simulate realizations of a multivariate Gaussian random field. I'm not saying it's the best method, but it's simple. So it says this, okay, you pick your grid points first. Let's say we've got a capital N of those. And you form your mean vector and your covariance matrix from the model that you've chosen. You've got your mean vector, you've got your covariance matrix. And if we want to draw samples from this multivariate Gaussian distribution, how do we do it? It's 3 lines of code if you're using MATLAB or Python. All you need to do first of all is draw NIID Gaussian random numbers. Put them into a vector. Let's call that bold xi here. As a vector, then that's a multivariate Gaussian with mean 0 and covariance matrix equal to the identity matrix. Okay, so it's easy to draw samples from this distribution just with standard random number generating. Question is then, how do we get the right covariance? You have to take your covariance matrix and factorize it. And there are various options. We'll talk about a couple of them in a minute. You take your matrix, assume that you can factorize it in the form VV transpose, where V is some matrix, and then claim all you have to do, take your sample of psi, multiply it by V, add on your mean, and then what you have is a sample from the distribution you want. Okay, that's like 3 lines of code if you want to code it up and actually do it. It's also about 3 lines of math if you want to prove that this has the right distribution. Make sense? It should be fairly easy to prove it has the right mean, has the right covariance, and also that it's Gaussian. Right? The key part is, can you convince yourself it's definitely Gaussian? Okay? So you can do that. Right? So the sticking point then is, well, how do we do this? And that's going to be the bottleneck in computations, especially if you've got a large number of grid points, n. So how many ways do you know to factorize a matrix in this form? Remember we said this is a covariance matrix, so it's got some nice properties. What nice properties does a covariance matrix have? Symmetric. Yeah, so it's not that it's a completely unstructured matrix, it has some properties. So to be strictly positive definite, we could use Cholesky factorization. We're familiar with that, right? Sometimes it goes wrong, especially if the eigenvalue is very close to 0. Or we could use the eigenvalue decomposition. So for symmetric matrices, it will look like that. Lambda is your diagonal matrix of eigenvalues. So if we just split that lambda into lambda or half, lambda half, which is well defined, as long as we don't have negative eigenvalues, which we shouldn't, at least in exact arithmetic, then this would be our V factor. Okay? Both of these methods are not particularly cheap if we have a large number of grid points. But let's just expand on this a little bit more, because this will be connected to something that we'll see later. So if I use the eigenvalue decomposition to get my V factor, then we're saying Z as this form, the standard random Gaussian sample multiplied by V add on mu. So you do linear algebra, and that's just another way of saying that. So my random vector can be decomposed effectively as the mean plus a linear combination of the eigenvectors of my covariance matrix with some random coefficients. And in front of each of these, we've got the square root of one of the eigenvalues. Okay? So n, capital N, might be quite large. Computing all the eigenvalues, all the eigenvectors can be computationally very expensive. if that number is large. So why am I emphasizing this? The eigenvalues will decay, right? And that's something that we can leverage in different ways when it comes to doing numerical computations. I'm not going to write down specific rates of decay, but if you were to just yourself, again, if you want to set yourself a simple computational exercise, you could take any of those covariance functions that I wrote down before, do this exercise, compute the eigenvalues on some grid and just look at how they decay. And broadly speaking, what you will see is the decay is related to the smoothness of the covariance function, right? Things like the correlation length that you've chosen will also have a role to play, right? So if we see that these terms decay, then we might be able to get approximate samples of our inputs working with fewer terms. And again, a simple exercise for you to try would be this one. So if instead of using the full eigenvalue decomposition, we just chopped it off after a smaller number of terms, right? So we're going to work with approximate samples. So if we did that, we would not be generating samples from this distribution anymore. We'd be making a crime somewhere. The question is, how big of a crime do we make? Well, we'd be using a different covariance matrix for a start. And the easiest way to assess the error is to think about the mean square error. Mean square error. So z is a vector, z hat is a vector, is my approximation. Right? So it's a relatively easy exercise to show that the crime is this. The error that you make is just the sum of the eigenvalues that you've neglected. So the faster those eigenvalues decay, the smaller little n you will need, right, to approximate this field well with this approach. Does that make sense? So we'll see something related to this later. I just want to emphasize the point that it's the decay rate of these eigenvalues that's really crucial. Depending on how much smoothness you have in your covariance model, you can get very fast decay rates, or you can get very slow decay rates. So for some problems, this may be an efficient thing to do to generate samples, others not so much. Just as a quick visual, is that bit visible at the back? So here's just an example with some covariance functions, some correlation length on some grid. So here I used a 65 by 65 grid in 2 dimensions. So that's 4,225 points. So my covariance matrix here is like 4,000 by 4,000. Right? So these days we can compute all the eigenvalues and eigenvectors, no problem. I'm just showing you one sample of Z. If I use the eigenvalue decomposition, I encode all of the eigenvectors. It's still pretty smooth because it's the Gaussian covariance. And here's if I only use 20 terms. Right? The eyeball norm, which is how you should never assess the error if you're a numerical analyst. You look at that picture and you look at that picture. Okay, if we're in machine learning, we'll just go, well, it's good enough, right? Numerical analysis, not so much. We'll make an error, and we definitely think and quantify the error. But if you take a step back, then what are we doing? If we chop this off, I mean, broadly speaking, we see that, this is really a composition of different modes, smooth modes and sort of oscillatory modes. This one has got like small oscillatory waves and is superimposed on top of this. So this definitely has more fine scale features than this one, right? But there's a lot in common. Okay, so we could use that method. Right, so these methods you could sit down and code this afternoon, right? There's no big deal here. These are all very classical methods. Those two methods, Cholesky factorization, eigenvalue decomposition, flexible, you can do them, but they're not particularly smart. They're not particularly smart because they don't actually exploit any other structure that you might have inside your covariance matrix. So if you noticed, all of the covariance functions that I wrote down were functions of the difference between the 2 points. Right? Actually, some of them were functions of the L2 norm of the difference between 2 points. But we say it's stationary if it's a function of x minus x dash. Right? And if we have stationary covariance functions, then we can do more because we have more structure. Right? So I'll just say in a nutshell that it's a sort of a big field of analysis here, that stationary random fields are closely connected to Fourier theory. And you should know that Fourier theory allows you usually to be able to do things efficiently when it comes to numerical methods. So I'm just going to sort of illustrate that with sort of just a sort of a very, in a very broad way. Again, here's a very simple exercise you could try. Let's say our domain was just one-dimensional. Let's say I have a stationary random field. So for this definition, what I mean by that is my mean is constant, and my covariance function is just a function of the difference between the 2 points. And let's say that the points that I use to evaluate my random field are uniformly spaced. So there's 2 conditions. I have a stationary covariance and my sample points are uniformly spaced. I claim that the matrix n is always, apologies for the pronunciation, Toeplitz. Does anyone know what a Toeplitz matrix is? Anyone tell me? Toeplitz matrix is one where if you go down the diagonals, on each diagonal the entry is constant. Right? So on the main diagonal it's the same entry. So if you look at them as an image, they'll be stripy. Right? So pick a diagonal, the entry down each diagonal is the same. Okay? 2 lines of math to show that. It's worth exercise worth doing. In 2 dimensions we get block matrices with block Toeplitz matrix with Toeplitz blocks. Picture's probably going to explain it best. So let's say I take my domain, let's say it's a square or rectangle, and I use uniformly spaced points in that direction, uniformly spaced points in that direction, and my covariance is stationary. Right? The matrix will look like this. So what does it mean to look at a matrix? So if you are a MATLAB person, put your hands up if you use MATLAB. Okay, not too many. Python? Okay, more Python people. I don't know what the Python equivalent is. So in MATLAB, someone can maybe figure this out and tell us tomorrow. You can basically give it a matrix and it will show you an image of the matrix. And what it will do is color code. It will show you like an image where each pixel will represent one entry in your matrix. And it will color the entries in the pixels according to the numerical value in that entry in the matrix. So if it's Toeplitz, it should look stripy. So if you just focus on that block right there, on each diagonal you see the same color. That's a Toeplitz matrix. Okay? So this matrix is block Toeplitz with Toeplitz blocks. What I mean is, you pick a block diagonal, it's the same block on that diagonal, and this diagonal, same block, but on each block is itself Toeplitz. Does that make sense? So at least visually, there's a lot of structure there. So if you use one of these other methods I talked about, you're not going to be able to leverage this structure. So the good news is, if you have this scenario, you can do smarter things to compute the factorization of your covariance matrix. I'll just go through it in a couple of slides. Again, there's going to be too much detail here for you to write it down now if you've never seen this before. I just want to try and convey the main point that if you have more structure, and you can exploit that structure, then you can do better, right, than these sort of naive methods that people often use. So there's 2 key things you need to know. If you have a Toeplitz matrix, so let's start in 1D, you can turn it into a circular matrix by adding rows and columns to it. So if Cn is your target covariance matrix and you want to generate samples from a Gaussian distribution with that covariance matrix, first thing you can do is just make a bigger version of it by padding it out with some extra rows and columns. So the next question is, what is a circular matrix? So a circular matrix, think about the first column. It's a special kind of Toeplitz matrix. You take the first column, and then the idea is that the second column you get from the first column just by taking the last entry of the first column, bringing it to the top and squishing it down. So the columns are like cyclic. Does that make sense? So the only bit of information you need to store a circular matrix is the first column. It's symmetric, right? Generally, right? So why am I telling you this? The eigenvalue decomposition of circular matrices has a special form that leverages Fourier theory. So that's all you need to know. Toeplitz matrices can be turned into circular matrices, and circular matrices can be factorized in a special way using Fourier theory. So I'll just go through it quickly. If you're interested in this, then you can follow up when you have a bit more time. So Cn, just keep your eye on that. That's the thing, that's the covariance you really want to work with. First of all, you make it bigger, and then you factorize this matrix, or you use Fourier theory. So if it's circulant, that's what the eigenvalue decomposition looks like, where W is the Fourier matrix, the complex value matrix, and lambda is still the matrix whose diagonal gives you the eigenvalues, right, of this matrix. But when it's circular, the idea is that those eigenvalues can be computed by only knowing the first column and then taking the inverse discrete Fourier transform. So that's the MATLAB command for inverse discrete Fourier transform. And that's all you need. Okay? So then what you do is you go back to a recipe. So you start from a sample psi, but this time you have to work with a complex Gaussian distribution. So it's very easy to simulate. You multiply by your V factor again. But in this scenario, this is complex valued. All you have to do then is take the real and imaginary parts of this complex random variable that you've just sampled, and you can show that they have this distribution. So the Gaussian, I haven't put a mean in here, so this is mean 0 at this point. The covariance is this circular matrix. That's not quite what we wanted. We wanted our covariance matrix to be Cn, which is like the top block of it. The good news is, just again with a couple of lines of math, you can recover the samples that you want just by reading off the first n components of these two samples. Right? So the cost of doing this is doing a multiplication with W, which is the Fourier matrix, so that's a discrete Fourier transform, and computing the eigenvalues, which is an inverse discrete Fourier transform. Okay? So today you have a new numerical method for doing this, and you can go to bigger grids and work with a broader class of models here, because the costs are now, rather than like n cubed with your Cholesky or your eigenvalue decomposition, are like order p log p, where p was the dimension of this bigger matrix. Now the slight delicate issue associated with this is how much bigger does this embedding matrix need to be in order for you to be able to leverage this method. And I would just say that is a bit of a delicate issue. And things like correlation lengths and smoothness class do play a role there. So this is not a method that was very well talked about until the 2000s, where people in the UQ community sort of rediscovered it again. Sort of, I think that's the earliest paper I know about, from like 1997, and then around 2010 and so on. Rob's gone. This is Ivan Gray and Rob Scheiko, so Rob's done master work there. I did some earlier work, as I said. So there's a technical report there, which is more computational in style. This paper has got some analysis in it. So this became a common way to simulate realizations of Gaussian random fields when you have stationary covariance matrices, because it can leverage the connection between stationarity and Fourier theory. Okay? So I apologize if that was a bit quick. I'm just sort of laying out for you that all these methods are pretty classical now. If your problem has the right structure, then you can kind of go to smarter and smarter methods. Okay. So you've got PDEs, you've got ways of simulating Gaussian random fields now on a grid. That's mostly not what I'm going to do. I'm going to not work with grid-based representations very much. The other thing you could do is say, okay, my random input is a function, and I'm going to stick in the function space world. I'm not going to use any grid-based decompositions. So I want to work with a series representation of my random field. Keep it as a function, and try and simulate it that way. So in case I forget to say this at some points, although I've probably already said this, I'm always going to assume that my domain is bounded. I'm always going to assume that the covariance function is continuous, right? And then I'm going to sort of make this assumption, which is important for what's coming next, that the random field I want to put into my problem lives in this function space. So what does that mean? If I cover up the omega bit, hopefully everybody knows what this L2 space is. It means I'm assuming that samples of my random field are at least square integrable as spatial functions, usually more than that. But if I pick a point in my domain, then it's living in L2 on this sample space, which means it's a second order random field, is what I said before. Okay, so how else might we represent our random fields if we don't want to work with grid-based representations. So here, if you like functional analysis, here's where we need some functional analysis. I'll just give you the key points. So we take the covariance function that you want to work with, right? Could be any of the models I wrote down before, or you might have some of your new examples, as long as it's a valid covariance function. And your domain is bounded and we have continuity. We now come along and define an operator, calligraphic C. So it's an integral operator, where your covariance function is now playing the role of a kernel. I'm going to call it a kernel when we use it in this setting. So now we think about the associated operator. So this operator, symmetric, bounded, linear, compact. And that's nice, because as an operator, it's got infinitely many eigenvalues and eigenfunctions now. Now we're working in the function space world rather than the matrix vector world. This operator has eigenvalues and eigenfunctions, infinitely many of them, right, which are defined through this equation here. So this says C phi is lambda phi. So that's an eigenvalue problem in the operator setting. And again, it's in classical theory, so if you want to look at it later when you've got some time, something called the Hilbert-Schmidt spectral theorem, which tells us the properties of the eigenvalues and the eigenfunctions of operators that have these properties. So in particular, the eigenvalues decay, what I said before. That's very easy to check in the matrix valued world. Function space world, this is much harder to solve, usually. But this theorem tells us that the eigenvalues decay. If we order them largest to smallest, they decay, right? And this is the crucial part. The eigenfunctions give us a basis for the range of that operator. So if what I want to do is create a random field with realization within this space, then I can represent each realization of the random field as a linear combination of these basis functions. And that's what we'll do next. The idea is then, for your covariance function, define an associated operator and use the eigenfunctions as a basis to represent it. Right? Everyone know what Fourier series is? You could think about this like as a Fourier series just with a special basis, right? Because these are going to be orthonormal basis functions. So I should say, different parts of the community do things slightly differently. I kind of came from the community that started by picking the covariance function and defining an associated operator. Other people just define an operator with the right properties directly. Right? So there are other people who just say, okay, let this operator be the inverse of some differential operator. And the same theory sort of applies as long as you have an operator which satisfies the conditions that you think. Right? So there's other ways to come at this. But basically, if you leverage that theorem, it says your random field can be decomposed. The important part is the thing in the box. So if you write nothing else down, maybe write down the equation in the box if you've not seen this before. It says your random field can be decomposed as the mean. So another way of saying this is the random field minus its mean can be represented with this infinite sum here. Right? There's lots of notation here. So the lambdas and the phi's are what we just said. The eigenvalues and the eigenfunctions associated with the operator associated with your covariance function. All right. So hopefully this reminds you of what I showed you before in the function space world. It's just now we've gone from eigenvectors to eigenfunctions. And instead of having a finite number of terms, we've now got an infinite number of terms because we're in the function space setting rather than the grid-based setting. And what are the random variables? So the way to read this is I've got a random field with a particular distribution and I can decompose it. Stands to reason that the coefficients have to be random and the distribution will follow from whatever the distribution of z is, right? So read it from left to right. So the psi i's here are defined this way. So if you stare at that a bit, you should just think, well, they're just Fourier coefficients. If you know that these phi i's are orthonormal with respect to the L2 norm, then these are just Fourier coefficients expanding z minus mu effectively. Z minus mu, you just expand that in the basis and then multiply up by the square of lambda I, that's just a Fourier coefficient. And it's random because every time you take a different realization, you just get a different linear combination of these phi I basis functions. This is called the Kahuna-Love expansion, or KL expansion. And this is a fairly well-used tool, I would say, in the numerical analysis community when we're solving PDEs with random input. Okay? So, key question is distribution. So if Z is Gaussian, this is the definition of your size, standard properties of Gaussian things tell you that these random variables are Gaussian. Okay? Here would be another simple exercise for you to try. If you believe me that this is the definition of these xi's, can you show that the basic probability theory that those random variables have to have mean 0? Well, we've subtracted out the mean of Z there, so that should be fairly easy to get. It's worth trying to show these that they have variance 1 and are uncorrelated. That's going to be really important, that this is a decomposition of this random field in terms of a countably infinite set of uncorrelated random variables. So that's what this gives you, a way of parameterizing, if you like, the uncertainty to a countable set of random variables that are defined this way. Right, so in general, uncorrelated does not mean independent. Right? So if I didn't have a Gaussian random field, I might be in trouble. But for Gaussian random fields, uncorrelated does give you independent. Right? Not sure. So this is a tool from probability, very similar to the eigenvalue decomposition that we looked at before, just in the function space setting. What I will say is that in sort of numerical analysis community, this is often used in slightly illegal ways. So what I mean by that is if we just cover up the Z and pretend we didn't start from something with a specific distribution, we often create random fields this way, and we just choose the distribution for the size. So we sort of reverse engineer a random field by using a sort of an ansatz, if you like, treat it as an ansatz, and then put in different sort of, I'm about to call it, distributions. But technically, it's a decomposition of a given random field with a given distribution, and you read it from left to right. Yeah.
How are the covariance function and the compact operator related? You showed an example of, I don't know, it was diffusion plus some identity to the alpha. Is that just some complicated example, or does that directly relate to any covariance function we know?
We can do this decomposition, so the proof of the KL expansion really relies on what we call Mercer's theorem. Right? So if people use this, so if I choose this operator to be the inverse of some differential operator, you can think about this covariance function as really being like the Green's function associated with that.
Okay, yeah, sure.
But people when it comes to doing numerics, people cook up all kinds of things that don't necessarily, start out. But that way, like, if you want to start there and kind of backtrack to this, then the covariance function would be like the Green's function.
Yeah. But the covariance functions we looked at now would produce like quite different differential operators, or not differential but compact operators.
Yeah. I'm not going to argue that you should use one way or the other.
Yeah. I'm just...
The point of view of numerics is just to say you can do something and then you can decompose it this way. Of course, the properties of the eigenvalues and eigenfunctions are going to be like inherited from either the operator or the kernel that you chose. Okay, so what I would say is we look at the function space rules, then we have flexibility now to do what we want with that random field, right? Okay, but we could, if we wanted to do sampling, then we could again just say, okay, well now we've got a function, we've got an expansion. If I did want to use it to do sampling, I'm not saying you should do this, then we could just as a thought experiment chop it off after a finite number of terms, let me call it j terms, and look at the properties of a truncated field. Let me call it z hat. Well, it's a function now, not a vector. So here I'm just kind of taking a particular example for you, and I chopped it off after 13 terms, 33 terms, 270 terms. Right, where the xi's, the first 13 xi's are the same, first 33 samples are the same. So hopefully just again the eyeball norm you can see this thing sort of converging, but hopefully you can see that like with 270 terms I've now encoded more of these small multi-scale features, if you want to call them that, than this. Chopping it off too early makes it smoother, effectively. But again, as a mathematical exercise, you could try and prove this, that the error that we make in the mean square sense, now in the function space norm rather than the vector norm, is just the sum of the neglected eigenvalues. So if we wanted to use this as a computational tool, the key question would be, how do those eigenvalues decay? And the good news is you can leverage functional analysis. People have been studying decay rates of eigenvalues of analytic kernels for a long time. And I just want to flag up some early work in this field that was done at my university, University of Manchester, that is often overlooked and forgotten about in this UQ world. Right? Generally, there's somebody who wrote papers giving explicit decay rates for certain classes of these kernels. I used to have lunch with him in those last few years of his life, and he was absolutely amazed that this work he did way back in the 70s and 80s had any sort of relevance to anything practical that people were doing these days. But these decay rates are sort of scattered all over the literature. I've just sort of tabulated there some of the rates for some of the covariance functions I've shown you. In particular for that little matter thing, you can see that the covariance rate there, the decay rate there explicitly depends on that parameter Q. Right? So the decay explicitly relates to the smoothness of that kernel that you've got. Let me show you a quick example here, one way that you can, another way, sort of engineering type way that you can assess the error in a truncated field is by looking at this sort of relative, so if you, sorry, there should be a Z. Z hat, Z. If you truncate the field, you have a new field which has a different covariance and therefore a different variance. You will underestimate the variance by chopping it off after J terms. If we have a constant variance, then the relative error in the variance can be written like this. And so again, it depends on the eigenvalue. So this is computable, because this only depends on the first J eigenvalue, right? Not the tail. Right? The mean square error, you need to know that the tail. This is something you can compute just from the first J eigenvalues. And I'm showing you here, right? So the theory says something about how the eigenvalues decay, but this is a computable estimate of the error in a different metric. So let's take the exponential covariance in one dimension. Theory tells me that the error I've just defined should decay like J to the minus 1, where J is the number of terms that I keep. So what I've done is I've done this computation where I'm taking more terms along the bottom here. And what do we see? So I've got 3 different correlation lengths. So this parameter L is kind of what I want to talk about here. Same covariance function, but I'm changing this parameter called the correlation length. So what do we see? So this is like the hypothetical slope of -1. This is when my correlation length is 1. That's half the length of my domain. This is 0.1 and this is 0.01. So this sort of order J to the minus 1 is hiding a multitude of sigmas, right? So really what we mean is we have an upper bound that looks like this, and this constant really depends on the correlation length. It's parameter L, so C really depends on L. So this is why with the blue line, we get stagnation. So it's not until J is large enough that we can sort of compensate for the fact that this becomes a very large constant when the correlation length is very small. Does that make sense? So if we say, okay, if I want to use these truncated coherent Lev expansions to represent my random field, how many terms am I going to need to keep? The correlation length is small, as you can tell in this graph. The smaller the correlation length, the higher the value of J that you will need to represent your random field well. Right? So let's say I'm happy with, like, I don't know, 10 to the minus 2 accuracy. So I'm here, the correlation length is 1. I can do it in this many terms, but if my correlation length is 0.001, I'm going to have to go way out here. Right? So the number of terms I will need to keep just at some point becomes unfeasible. So small correlation lengths, if you take away nothing else, bad. It becomes very challenging to simulate random fields or to represent them when we have small correlation lengths. Okay, and I realize I only got 5 minutes, so let's just kind of, when you skip over some slides, let's just go with basic Monte Carlo. So we've got things that we should now be able to put together right? So we've got PDEs, we've got certain inputs, we've now got two different ways to approach representing the random inputs to my field. I could either go with a grid-based approach, or I could use one of these coordinate type things and represent it as a function. I'm going to go with the first approach, the grid-based approach. So I've got my simplest PDE model that I had, it's my groundwater flow model. Now I said I was skipping over all that sort of assessment of is my problem is well posed, what are the function spaces and so on. If you write down the variational formulation of this problem, then very similar to what you saw this morning, there'll be some conditions on K that need to be satisfied for the weak problem to be well posed. And in particular, you'll need it to be positive and bounded. You need any sample of this thing to be positive and bounded. So if I just use a Gaussian random field, those are going to go out the window. This is what I mean, you cannot just stick in any old random field into your model and expect everything to be okay. So, something we could do, we could take the exponential of a Gaussian random field, so we say it's log normal. That would ensure that every time I draw a sample, it's sort of not negative, right? Hopefully bounded away from 0. So I'm going to work on a rectangular domain this time. I'm just showing again samples of a Gaussian random field. I'm going to take the exponential of this as the input to my model for a covariance function, which is giving me samples which are less smooth, a covariance function which is going to give me smoother samples. So for the spatial discretization, I'm using a standard finite element method. So remember what Rob said this morning. When we use a finite element method, we're going to have to think about the mesh that we choose. And if we have a small correlation length, we're using a standard method, h-bet, to be very small to capture the variation that we've got. I'm using something called a Rayleigh-Thomas finite element method here, but that's not important. So, standard Monte Carlo, standard finite element method. So what do? You just have to have a way to generate samples of the random inputs to my problem. Talk about any of the methods that we talked about. Right? So z hat is just some approximation to the random inputs of my problem. You stick them in your finite element code. For this model, you have to solve linear systems that look like this. And what comes out are samples of your PDE solution. And the Monte Carlo method just says you just do that m times, m is your number of sample, and you average the results. That's easy to do, it's the quickest way to do computations. It allows you to reuse your finite element code with next to no modification. People say it's truly parallelizable. And the key thing is that it doesn't really matter whether we sampled our random inputs with a grid-based method or with a function space method, whether they were linear, non-linear, whatever. This method doesn't care, it's just a sampling method, right? As long as your finite element method can read in the samples of your inputs in the way that you've simulated them. Okay, so I've just done a fluid flow simulation. Probably can't see the arrows, so I've computed a mean flow field here. And then what I might be interested to say in this kind of model is tracking the path of a particle that's released into the flow. So, for instance, I might start there. And then 500 different simulations, 500 different flow fields. The particles go all over the place, so maybe you can think about a potential application for that. So hopefully I'll get through this side. So what's wrong with the standard Monte Carlo method? I'll try and get through this and then maybe we'll stop. So I think everybody knows, but it's worth spelling it out. So just to simplify things, suppose what I'm actually interested in is a scalar valued quantity. That's not what I'm interested in. I want to compute a spatial velocity field and a pressure field, but just to simplify the analysis, let's focus on a scalar valued quantity. Pick a point in the domain, let's say it's this one, and let's say I'm interested in computing statistics of the pressure at the point. So then x, capital X here, is a scalar valued quantity, and it's a random variable because the input to my PDE was random. And so if I want to estimate the mean of that random variable, with a Monte Carlo finite element method, then what am I doing? I'm generating samples not of x, I'm generating samples of some other random variable, let's call it xh hat, and it's an approximation to x in two ways. One, because I've done my spatial discretization with my finite element method, and the other way because I've had to approximate my random coefficients somehow. So I've got a discretization error in there. Samples of xh hat are not samples of x. When I compute my estimator, I'm computing averages of samples of this random variable rather than the one that I really want. So now we ask ourselves the question, let's suppose I want to guarantee that when I use this method, I have some error control. And by that I mean, let's suppose we want the root mean square error to be less than some tolerance that I pick. Right? So a numerical analyst's dream is you pick a tolerance and your method just does its thing and gives you an approximation which is guaranteed to meet that level of accuracy. So let's say we want the root mean square error between the mean of x and the mean of the thing I'm really computing to be under control. Here's a very simple exercise that's worth doing before Fabio Nobile gives his lectures later in the week when he's talking about the multi-level Monte Carlo method. The mean square error, so it's always difficult to work with that square root there. So if you just square this up, then you've got mean square error. Right? You can show that the mean square error has got two components. One associated with using Monte Carlo sampling to estimate a true expectation, and the other is coming from your finite element sampling method. This one's typically called the bias. So this is going to depend on the accuracy of your finite element method, how you've estimated your coefficients. This one is to do with the fact that you're doing Monte Carlo sampling. Okay, so this is often called the standard error. This is usually called the bias. So you've got two contributions to the error. Right? So there's no use making your finite elements mesh really, really fine to make the bias small if you didn't use many samples, because that means the standard error will be large, right? So you've got two contributions to the error. If you want the overall error to be small, you're going to have to control both things. Similarly, there's no use just taking a bazillion samples, right, to make this small if your finite element mesh was too coarse to really resolve what you want to see. You've got to balance them somehow. So try and figure that out. There's a couple of lines of math, right, and some basic probability theory. So what we're really interested in is how much work do we have to do to implement the method to ensure this is true. So that means how do we choose our H and how do we choose our number of samples? We need some rule to tell us, to guide us, how we choose these things to get the level of accuracy that we want. So for this is where we need the a priori analysis. So for our finite element method, we'll need to assume that we have some bound like this. So remember we saw this earlier. And remember, we think C might be hiding some stuff, but we'll just ignore it for now. Alpha will depend on the regularity of my PDE solution. So it might be 1. We've used piecewise linear finite elements and everything's fine. And then we say, okay, so this is how this is going to behave as I refine my mesh. This thing depends on m to the power minus 1. So if I want mean square error to be less than root epsilon squared, then this is how h and m are going to have to scale, right? Sorry, at this point I'm just saying this is how the first contribution to the error behaves as I change h. This is how the second contribution to the error behaves as I change m. We now think about the work we have to do. So we want this to be true, we want the mean square error to be less than root epsilon squared. So this tells us how h and m need to scale with epsilon in order to meet that requirement. So h will need to scale like this. So regularity is important here. That will affect how h needs to scale as we change the tolerance. And this is the standard Monte Carlo sampling scale. So this means, okay, think about the work. In a standard Monte Carlo sampling, what we do is we do m samples, so whatever m is, and then we have to solve our linear system. So the cost of doing linear algebra is often overlooked in these sorts of uncertainty assessments. The bottleneck whenever you do a finite element solve is to solve a linear system. So if you fixed your mesh, let's say you've got NH equations, even if you can solve that system in the amount of work that scales linearly with the problem, then in d spatial dimensions, that's probably the best you can do. So put in that for m and that for h, and this is what you end up with. The work is going to scale with epsilon like this. So what does that mean? So let's say d is our spatial dimensions, let's say that's 2. Alpha's 1, that's epsilon to the power minus 4. So what does that mean? Everyone remembers this when we talk about Monte Carlo, right? But actually, if you think about the work you have to do to ensure the overall error is under control, the cost of generating your samples and the accuracy of your finite element method plays a role too. And put everything together, this can be really, really bad. So epsilon to the power minus 4, what does that mean? Reduce your tolerance by a factor of 10, the work has to go by a factor of 10,000. And if you have low regularity, alpha might not even be 1. And of course, there are constants hiding in here which can depend on things like the correlation and so on. So it's really, really bad. So I'm going to skip over these. I will put them in the slides so that you can read them at your own leisure. I'll just say Fabio is going to talk about one potential remedy to this later in the week. So if you've already got in your head a good understanding of the basic Monte Carlo method, that would be a good starting point to build from. Okay, so we have a break now, so I'm going to stop talking. You can get to the end, but I'll just pick up after the break. I think that's a natural place to start now. Okay, so feel free to ask me any questions over the coffee break.